Number 6.
So our main point would be the time between drop depends on the water flow rate. And so here's the phenomenon. So when a faucet leaks, the water droplets fall from the faucet opening in a specific pattern. So the time interval between these droplets, they change with variation in the water flow rate, leading to both regular and irregular behavior. So here's my theory. So we think it is influenced by 4 factors. So mainly gravity, surface tension, dynamic pressure, and viscous force. So for gravity, the drop gets bigger. The gravity also increases. And when the flow rate increases, the gravity also grows faster. And the next one is the surface tension. So it comes from the forces between liquid molecules. And this is distributed along the contact edge between the faucet, just like these, the blue arrows. And the vertical component of the surface tension balances the gravity. So because the surface tension is influenced by the temperature, so because we control the temperature, so this remains unchanged. And our next third one is the dynamic pressure. And the definition of it is the pressure caused by the movement of a fluid. So because our drop falls down, so it is mainly depends on the influence of the gravity, so it is downward. And our formula is from the Bernoulli's equation approximation. So here, this is dynamic pressure, and this is liquid density, and this is the velocity. And this is the formula from Newton's viscosity law. And this is the shear stress, and this is the dynamic viscosity. And this is the velocity gradient. So as the flow velocity increases, the shear stress also rises. And this is our next formula. So this is the viscous force. It is equal to the shear stress times the effective area. So as the flow velocity increases, the shear stress also rises. So the viscous force increases. And here, due to the variation in our flow rate, the flow velocity also changes, leading to different degrees of influence from these four forces at different flow rates. So we divided our process into 3 stages. And here, for the first stage is the low flow rate, which is regular dripping. So here, when we look at the force, here the gravity exerting a downward pull, and the surface tension plays the primary role in this section. So it's stabilizing the droplet shape and its drip time interval. And here, the dynamic pressure and the viscous force, they have a comparatively minor impact. And in the stage 2, which is moderate flow, and also the transition mode. And here, gravity becomes significant as the droplet becomes bigger. And here, the surface tension remains constant, but it has a reduced relative effect. And here, the dynamic pressure and the viscous force then starts to increase. And in the last stage, which is high flow rate, and it is chaos. And here, gravity exerting a strong downward pull because the droplet is reduced. And the surface tension here with a minimal influence. And here, dynamic pressure and the viscous force, they are very strong, and they cause the liquid shape to be irregular. And here's our experiment 1. So here are my variables. My independent variable is the flow rate, and my dependent variable is the drip time intervals. And here's my setup. We've got a faucet, and for the water flow rate, we've got a measuring cup, a scale, a timer. And for the dripping time intervals, we have an Arduino, a breadboard, and a sensor, and also a displayer. So here's my procedure. We weigh the mass of the empty measuring cup. Then we measure the flow rate. So we fill the measuring cup with water, and every 30 seconds we weigh the mass of the water and divided it into 30, and this gives us the flow rate. And our third step is to measure the drip time interval, and we do this step during we measure the flow rate. So here is our model schematic diagram. So this is the breadboard, and this is the displayer, and this is the sensor, and this is Arduino Uno. And here's the detailed pin of our Arduino Uno and the sensor. And this is our experimental setup for the drip time interval. And this is our water barrel, and this is the faucet. And the sensor is right under the faucet. And the measuring cup is also under the faucet. So when the droplet passes through the infrared sensor, the sensor emits infrared light, so which is reflected back by the droplet. So we can get the drip time interval data. So this data is displayed on our displayer, and we use this software. And here's our data. So we plug our data into a drip time. We plug our time interval data into a phase diagram. So the x-axis of this is Tn, which is the time interval of this droplet. And the y-axis is Tn plus 1, which is the time interval of the next droplet. And this kind of phase diagram is usually used to observe for the periodic or the chaotic behavior. So when it looks more like a single cluster, it is more periodic. However, when it is more scattered, it is more chaotic. So for experiment 2, so because we have limited equipment, so we use Python and matplotlib to do the computer simulation, and we use these 3 equations for 3 stages. And so for the first stage, we use a linear equation, which is this. So here, the time interval is proportional to the flow rate. And from our data, the fitted coefficient x is smaller than 0. So here we can know that when the flow rate increases, the time interval decreases. And this linear equation has a negative slope. And for the stage 2, we have a moderate flow, and we use the differential equation. And for here, the droplet's time interval is no longer independent, but influenced by the previous droplet. So the current droplet's time interval is influenced by this, which is time minus delay time, stands for the time interval of the next droplet. And the R is the control parameter that determines the system's behavior. And here are times Tn, they are the growth factor. So here, when the larger R is the influence of the Tn is amplified, so causing the time intervals to vary more dramatically. And here, 1 minus Tn is the nonlinear suppression term. And here's R. R equals to A times Q plus B. And here A and B, they are also Phillips coefficients. And here A is bigger than 0. And here, we can know that when we got higher flow rate Q, there is higher R, which is more chaotic. And so here's our data. We plot it into a diagram like this. And the x-axis is the flow rate, and the y-axis is the time interval. And the x, the black process, they are the real data we get. And the lines, they are simulation results. And here's our discussion. So we will discuss our real data plot into the phase diagram, and also discuss about our simulation results. So here, based on the distribution of the points, we divided into 3 stages. And here, for first part, we got regular pattern. It is stable and predictable pattern. So when we look at the phase diagram, it looks more like a single cluster, which is more periodic. And here, when we look at this chart, we can see that it is the simulation result is the blue line, which is linear equation, and it is very regular. And for the part 2, the transition pattern, and this stage marks the shift from the regular behavior to irregular behavior. And here, there are the green one and the yellow one. They start to gradually spread out, so they are more irregular. And the drip time interval gradually becomes irregular, just like the green line here. They start to fluctuate. And for the part 3, which is periodic pattern chaos, this is the final stage of our experiment. So here, the definition of chaos is a dynamic behavior that is extremely sensitive to the initial conditions. So here, the dripping time intervals become highly irregular and very hard to predict. So here, it is the orange one and the purple one. So they look very scattered on this phase diagram, which means they are very chaotic. And so here, when we look at this chart, it is the red line. They are very irregular and showing chaos. So here comes my conclusion. The faucet dripping phenomena were divided into 3 stages. And the first stage, it follows a stable and predictable mode. And the second stage is transition pattern. It marks the shift from regular into irregular. So we use this DBE equation to our simulation. And for the third part is the chaotic pattern. So it is now periodic, and because it is very highly sensitive to initial conditions, so it is very hard to predict. And we use the logistic map this for our simulation. And thanks for your listening.
Okay, first of all, thank you for your report. Now I have 2 questions. First of all, can you turn to page 49? Sorry, 47. And there's a graph of the different stages.
This?
Yes. So how did you find the boundary between the different phases?
So you can see that.
Yeah, how did you find the numbers where you separated the different phases?
Because we use the computer simulation, so from the result we can easily
Okay, I'll give you a figure about that later. Okay, so can you turn to your setup? Can you turn to your setup? So I want to ask, what is the maximum precision of your sensor? So how many data can it collect in a second, for example?
You can collect over 100.
Do you think that's enough?
Yeah.
Okay. So what's the range of sensor that do some of the droplets that maybe they have different directions and may drop the sensor's range? So does that happen?
No, we don't think it happens.
Okay. What's the distance between between your sensor and the faucet.
You mean here?
Yes.
It's about 1 centimeter.
Okay, so under 1 centimeter, does the droplets always form at the 1 centimeter?
Yeah, it is.
Thank you. Now, so how do you control the water pressure?
Oh, it remains the water level the same.
How do you? Okay. Thank you. Arduino sensors to gather their And they only had one parameter, which was the flow rate. And so the result was that they found 3 distinctly different regimes. Next, onto the strength and suggestions of the report. So first, I think that the reporter gave a complete qualitative theory about the phenomenon. So the reporter qualitatively analyzed the different forces acting on the surface and also compared their intensity, so that we can know which force is the main cause of the phenomenon. And also, the reporter did a lot of experiments and tried to use some simulations to compare them with the experimental data and separate the 3 different regimes. But under the suggestions, first of all, I think the reporter could better control pressure or perhaps explain how they control the water level because there was no explanation of this in the report. Next, onto the boundary between the different phases, the reporter did not explain why those phases happened. I think that the reporter should at least qualitatively analyze how the different forces interplay with each other, how they might cause the different phases to happen. And while there was some qualitative and comparison between the different forces and their effects, it was only limited to qualitative comparisons, and there were calculations or values of the different forces given by the reporter. So perhaps some quantitative comparison could be shown. And also, in terms of the simulation, the reporter mentioned that they solved some differential equations. However, I don't think the reporter did manage to show the equation in the report, which I think could be slightly improved in order to improve our understanding. And also, perhaps they could also include their code in this report and talk about how it works. And also, I think that the reporter could better explain how their experiments work and how they went through the procedure for each experiment. And also, while the reporter, I must commend the reporter first for trying to define the boundaries between each regime. There were no quantitative boundaries or values between the different regimes, depending on the flow rate, which I think could be improved. And so there was also an explanation as to how the reporter managed to find the boundaries, and that's all my report. Thank you. And now I'm going to let the reporter on the stage for the discussion section. So continuing from the short question, can you go back to your setup? Okay, so first about the water pressure. So you mentioned that you control the water level, but can you explain how you do that?
So while the water decreases, we add more water to it.
How do you add more water into it?
We use the water to pump.
So you pump water into the barrel while water was dripping. Okay, so does the motor pump water into the barrel at the same rate as the faucet drips water out? So did you measure the flow rate and compare that with the motor?
Oh, we do control, and we make sure they are the same. So we didn't put this in our presentation.
Okay, so can you explain how you control the flow rate? How do you control the flow rate first?
Okay.
Yeah, how do you change the flow rate?
So here's the faucet. So we adjust the faucet.
Okay, so and then you, how do you measure the flow rate when you measure the mass accumulated in the cup in 30 seconds? Is that correct?
Yeah, because we already control the environmental conditions. So we think we use the average flow rate, it is okay.
Great. So can you turn to the graph where you talk about the different regimes? Okay, so did you manage to, for every data point, manage to control the motor so that the flow rate was the same as the faucet?
Yes.
Oh, okay, I think that's great. And next, let's talk about the distance between your faucets and the droplets. So did you ever observe some perhaps columns forming under the faucet?
Sorry, can you say that again?
So, let's say this is a faucet. So I think that maybe when the flow rate is large enough, perhaps there will be a string here, a column here, we can call it the column, and perhaps the distance where the droplet begins to form will change. So did you ever observe that?
Yes, and we make sure it is far enough for our sensor to get the right data.
Okay, so did you measure how many column was?
The real data is smaller than 1 centimeter.
Okay, so it was always smaller than 1 centimeter.
Yeah. So our sensor can get the right data.
Okay, thank you. So you also mentioned that so only droplets were in the center, and so they do not leave the range of the center. Is that what you said?
Yes.
Next, I want to talk about your theory. Can you go to your theory?
You mean where?
Okay, if you want to talk about the simulation, so you mentioned you saw some differential equations. So can you go to that page? In the simulation. We're, so the part where we talked about the simulation, I think
Which state?
you talked about using Python to simulate the data. Okay, yes, so can you go to the page where we talked about stage3? Okay, so what's this equation? Tell us that, like, how do you know that it applies to this faucet? And yeah, so how did you know that it can apply to this faucet? Or for a better question, how did you apply this to the faucet?
This is from, we can come after this from our phenomena and it fits our theory.
So you derived this yourself?
No, it is in the reference.
Maybe perhaps you can include some of these references. Also, you mentioned that you try to solve this differential equation, is that correct?
Yes.
So did you manage to show the property in your presentation?
Sorry, what did you say?
So did you show the code in your presentation?
No.
Okay. Now, so maybe you can show that in the future.
Yeah.
So I think it will help with the understanding. So as for phase 3, you mentioned that you use the logistic map to compare it with the faucet. So how does the logistic, what do you think the logistic map can apply to this faucet?
Because in the high flow rate, it can be applied to.
Okay, so in the high flow range. So how high is it, that flow rate? So can you give me a number?
I can't give you the critical number, but you can see that in our result, in our diagram. So when we apply our equation into these, when the pattern starts to become irregular, it means it is on to the next stage. So
Okay, so but like for example, with this part, so before this point you use a linear like to simulate it, and after this point you use the differential equation to simulate it. So where did you find this point?
because after our picture started to crash.
Yeah. So you mean that your code starts to crash after this point?
Yeah.
And like what's that point? So is there a
We didn't write the critical number in our presentation, so
Okay.
maybe we can use that in the future.
Okay, thank you. As for the chaotic stage, so is it entirely chaotic?
Yeah.
But you mentioned that you use the logistic map to model it. But I believe that, for example, with the logistic map, as it is the bar and in the equilibrium condition, and so I believe that even in the chaotic regime, there are certain Okay, so I can come back to that phase diagram, the graph where you show the different regimes. Okay, so so does the code crash at this point as well? Because from your data point, it seems that even in this stage, how scattered they are seems to be quite similar.
But they're scattered, but they start fluctuating in the chaotic part.
What do you mean? Okay. And what do you mean by chaotic?
You mean the definition of chaos?
Yes.
Chaos means the system's result is highly sensitive to the initial condition.
Yes, but how did you know it was chaotic? So did you perhaps try to quantify it? For example, by the exponent you can actually quantify that it is chaotic. So did you ever try to compute it? Yeah, did you ever try to calculate it? Or try to prove it is chaotic?
The data there.
Okay, thank you very much. So for my conclusion between me and the reporter and our discussion, first of all, we discussed the setup. So they used a motor to control the water level and the water pressure, which I think is a great solution to the fluctuating water level. And they also managed to measure the column length and prevent the sensor from being unable to measure, for example, the column forming and preventing the sensor from accurately reading the data, which I think is very commendable. However, in terms of the diagram, we're going to talk about the different flow rates. First of all, when I asked them, they did not seem to adequately explain how they were able to find the boundary values. And yes, and so they also were not able to give a value in that. So thank you.
Okay, I'm going to ask the reporter about page 35. Okay, so you have the graph that this line is linear and this line is about the moderate speed of the flow rate.
Yeah.
So what is the boundary of the slow speed and moderate?
You mean the critical value? In our presentation, we didn't get the critical value. But when the system started to crash, when we do the simulation, and that's the boundary. But we didn't get the critical value into our presentation, and we will include that in the future.
Okay. And then what is the boundary of the moderate speed and higher? Because the moderate speed, you have like 2 or 4 interval time. But in the higher speed, I'm asking, what is the boundary?
The answer is the same as the previous one.
Okay, and then I'm gonna ask what is your opinion of the question?
You mean?
The boundary.
Yeah, I think they did not seem to give a value. So yeah, so I think experiments may need to be done to find it.
Okay. And then the next question is, can you turn to the theory part?
You mean which part? The simulation or the phenomenon?
The first part, the theory part. The surface tension. So you said that the surface tension can affect the water drop. The water drop when it is on the slope.
No, it always affects the water drop, but it is more primary in the first stage, and it will become more minor in the
High speed.
yeah.
Okay. And next page. Okay, the next page, you said that near the type of the output, what is your output Okay, so I'm from Team Selecting and I'm the reviewer of the problem 6 dripping faucet. The problem statement is the leaking faucet develops interesting dripping patterns where the time between drops depends on the water flow rate. Investigate the phenomenon and study how it depends on relevant parameters. The key points we found that is the chaos and the flow rate. The overview of the report. From the theory part, they use gravity, surface tension, dynamic pressure, and vicious force to analyze the phenomenon. And they list different phases like the slow phase, the moderate phase, and the higher speed phase. For the experiment part, the flow rate, they use the flow rate, and they use sensors to get data. And they did computer simulation to get the graph. For the conclusion part, phase 1 is a single period, phase 2 is double period, and phase 3 is chaotic. The remarks to the reporter. First, the advantages. Analyze the force theory, and they do simulations. Use Arduino to make measurements more accurate, and they introduce the difference between theory. For the suggestion, they didn't combine all of the theory and only one parameter flow rate. And remarks to the opponent. The advantages. They observe details of parameters and setup, and they give many suggestions for the reporter, and express his question accurately and detailed. For the suggestion part, they should list a discussion order or it will be complex and messy. Okay, these are the important discussions. So first, how do you control the water level? The reporter answer is they use mortar to add water on the same flow rate. The opponent answer is they accept it, but the reporter didn't show that. The reviewer answer is that is a good way, but they should use the photo to explain more. Next, why is the data before 0.2 seconds is linear, but not after 0.5 seconds? The reporter answer is they cannot detect the boundary, and the opponent accepts the explain. And for the reviewer's answer is they can measure the different period cycle, like the two interval times or the 4 period interval times. And then how to measure the time between two drips. The reporter said they said Arduino is accurate enough, and the opponent said that is acceptable. The reviewer answer is they can use multiple methods to double check. And that's it. Thank you.
And the reporter from variable 1. And here's our concluding remark. So the opponent asked about the water pressure, and we said we control the water level by a pump and while the dripping falls. And he also asked about dripping flow rate. So we say our monitor is sensitive enough to ensure we can use the average flow rate. And also we can control our environmental conditions. And for the simulation, we use the theory from references, and we compare the simulation result and the experiment result. And for the boundary, when our code crashed at the critical value, and that means the process turned into the next pattern. And for here, he suggests us to give the critical value, and both reviewer and opponent suggest this, so we can do that in the future. And for the logistic mapping, we discussed on the whiteboard, so I can investigate that missing part in the future. And for the definition of chaos, which is asked by the reviewer, and we say it is the system's result is highly sensitive to the initial conditions. And he also asked about the surface tension, and we said that it affects during the entire process, but it has a significant effect in the first part. And in our report, we have divided the dripping faucet into 3 stages. So the first one is the most regular, and the second one is the transition mode, which is from regular into irregular. And the third part is the chaotic part, which is highly unpredictable and very irregular. So this is my concluding remark. Thank you.
Okay, so any questions from the group? Reporter, page 35, please.
sort of straight line. The slope go down, but becomes flat. Like this one. Okay. And the third region is the fast flow. It becomes oscillate. The rate actually even sometimes go up. What's going on? Make a guess. What's going on? Why? Not only just oscillate, but sometimes goes up. What's going on? Just make a guess.
So maybe that. So because it's the Corey mentioned that it's chaotic. So if it's chaotic, then maybe any change in the flow will cause differences in the final time interval we managed to observe.
Okay. How about you? Why it goes up? It seems slow becomes the flow becomes slow. Why is it goes up? Make a guess.
In my opinion, I think that is the mg and the surface tension to mix up. It's because that
Just what's going on the water flow? Make a guess.
in the moderate flow rate, the water will get the surface tension more less, but
So in my opinion, I think maybe in this heat, the viscous force and the gravity and the foreign force I mentioned in my report, it somehow becomes, it makes the...
Let me give you a hint. The water flow goes up means the water flow rate becomes slower. It means the water doesn't want to go down. Is that right? So then guess what happens? The water doesn't want to go down, so otherwise the slope should be negative.
So I think maybe it is because of the surface tension.
What's going on the water flow?
So the water...
Yeah. How about you?
I also think that
Okay. If you want to add a few.
Okay, so maybe it's because in our range sometimes like the viscous force may sometimes increase, so they kind of pull back the water, and
Yeah, that's my question. So what's going on?
so I think that maybe it's because the viscous force and the surface tension sometimes become more dominant, and also
You
that
think the turbulence appears? Okay, that's what it's chaotic is non-linear, so usually the water flow becomes turbulent. But the water doesn't want to go down because the backwater pushes too much, so it becomes turbulent.
Questions from the other two? May I ask? I think you mentioned about the chaotic region here. I'm a little bit wondering about how do you compare this data. And you mentioned the initial condition will change and happen here, right?
Yes.
I'd like to know, you also did some work on this part. What's the initial condition? What's the change of the initial condition? Please, on the review. Please, review first.
So the initial condition is about the period that when the water drops, the upper part will lift up and
What's the, okay. And how about you?
yes, so I think that maybe the water pressure will change. And also, when they drop that force, the water, maybe some of the column and emission will be subjugated and will affect the water.
You did an experiment. Tell me what is the initial condition you have changed.
It's about the previous droplet.
Tell me related to previous problems.
Yes. So it is also there.
Okay, thank you very much.
Time's up, so let's do this, please.
Water. Six, seven, 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 eight. And the opponent. Five, seven, five, seven, five. Then review. Six, six, five, six, five.